All right, welcome back, everybody. So we're here for our second video, the next video in our AP Physics C content and examples. This topic is topic 1.2, which focuses on displacement, velocity, and acceleration. That is the actual name that comes from the course and exam description. Now, interestingly enough, however, it is not exactly is not the same as it kind of goes hand in hand, really, I think, with topic 1.3. Honestly, I know that I said in the previous video that we weren't going to be combining topics and we would just do at most one at a time. But the more I think about it, the more I realize that some of these topics are a little bit more interconnected with each other, and therefore probably makes some sense to cover together. I don't think that there's going to be too many where we kind of combine multiple topics. I can maybe think about forces. We would maybe do a little bit with that. Likewise, with thinking a little bit about perhaps in rotational motion. But by far and large, right, most of the topics thankfully just stick to one concept. Here, however, I find that like the topic 1.3 in the course exam description is representing motion. And so in terms of thinking about that, that's actually where you start to get into the visual representations, the equation representations, whereas topic 1.2 more focuses on definitions. And I feel like if we just focus on definitions, it's going to be a very short video. So, we may as well just kind of build in this representing motion. And then if we need to take a look at some examples in the next video instead of moving on to the next topic, we can do that then. So let's take a look, right? We know what displacement is, though. We know what velocity is. We know what acceleration is. Right? I'm not going to write that down, but displacement, of course, is just how far we ended from where we started. Right? Velocity tells you it tells you how fast you're going and in which direction, and then acceleration essentially tells you how strong of a push you're experiencing and in which direction as well. Right. And I know that sounds very similar to forces, but going back to Newton's second law, net force is related to acceleration. It does essentially describe your overall push, right? But it's more the observable effects of that push, of course, right? Acceleration is not the exact same thing as force, but they are related to each other. So again, I like to think of acceleration as essentially a visual representation of which direction you're being pushed, and how strong that push affects you, how strongly that push affects you then as well. So if we wanted to take a look at those mathematically, there are a couple of equations that we have back from AP Physics 1, right? You're probably used to seeing something along the lines of this, right? Velocity is equal to displacement over change in time. But that only refers to average velocity. That does not hold for everything. That does only hold for average velocity. So it tells you essentially, if I were to go from my initial point to my starting point directly, and it took me delta t amount of seconds to get there, right, how fast would I need to go if I essentially took the shortest possible path to get there? And then likewise with average acceleration, right? Acceleration is equal to change in velocity only over change in time. That also only holds if in the event of talking about average acceleration, right? If I started at rest and I wanted to speed up to say 5 meters per second in 2 seconds, right? If I wanted a constant acceleration in that entire 2 seconds, what would that acceleration need to be? So for example, right, I could start at this point right here. We'll call it start, for lack of better name, and then we'll maybe go to end right here, right? So if I were moving with a constant velocity, right, then and I wanted to take essentially the shortest possible path to get there, right? All I have to do is, that is not a straight line. I apologize. There we go. All I have to do is draw a straight line between beginning and end, right? I say how long I want it to take me to get between start and end, and then I divide that displacement, that path length, because it's the shortest path length between the two by time, and I'll get my average velocity. Again, average velocity just tells you if I wanted to go at the same speed, the same velocity the entire trip, what would that velocity have to be? And then likewise with average acceleration then as well. However, we do know that, of course, if you're getting from start to end, you're most likely not going to be going in a straight line in the real world. Depending on where you live or where you're trying to go, where you're starting, right, what mode of transportation you have, you could end up taking a super wobbly path between the starting and the ending point right there. And in that case, your velocity is not constant. You're changing direction the entire time. Your acceleration is also not constant because at some points you're being pushed towards the top of the page. At some points you're being pushed towards the bottom. Right, you're changing direction from going up to down. So your velocity is changing. Right, you're constantly curving, and then your acceleration, right, is causing you to change the rate at which you're moving up or down. Then. So what all of that gives us then is that does give us two very strong definitions for instantaneous velocity, which tells you the velocity at any point in time, and then likewise with instantaneous acceleration, right? So we just call those velocity and acceleration for short. If you are asked to calculate average velocity, it will specify the word average. Right, but if you're just asked to calculate velocity, that talks about a velocity at one point in time. That is instantaneous velocity. So I'm not going to write VI for instantaneous. That would get confusing with initial, nor am I going to spell out instantaneous. I'm just going to call it V for velocity. And the equation for that is actually the derivative of position with respect to time. Right. So if we're actually trying to make that one dimensional, right, then that would just be the x component of velocity would equal the x component of position dx over dt. And then likewise with acceleration then as well. Acceleration is actually the derivative of velocity with respect to time. Again, these are vectors in general, but you can just focus on one-dimensional motion. And that's in fact what we're going to do in this video. So we can drop the vector signs and just say that the velocity for one-dimensional motion is equal to the derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time. And the question might be, what is a derivative? It represents the slope of the tangent line at a given point for a graph. So I'm going to go ahead and draw a position time graph right here just to show you what I mean by that. Right, so we got position, we got time, Let's see. I'm going to scroll down a little bit there. There we go. And let's say that our position time graph looks something like this. Well, if I wanted to say calculate the velocity at this red time right here, we'll call that t0. How am I going to do that? Well, what I have to do is I have to actually draw a line that intersects with that curve right at that point right there. And the slope of that red line that I drew, that is the velocity of the object at that given point. And that does seem like it's a little bit messy, right? If you haven't done calculus before, that seems like it's going to be very messy. But the good news is that derivatives have a bunch of rules that they follow. And those rules are actually on your equation sheet. The rules that you're going to have to apply differentiation or derivatives to, right? The differentiation is essentially the act of taking a derivative. Then all you have to do is go to your equation sheet and use the rules that they give you to do so. So as an example, let's go ahead and create a function here. Let's say a ball moves to the left, to the right, along the x-axis, let's say, along the x-axis with position x of t, so this is position as a function of time, is given by, let's say 5 cosine of 2t just for fun, right? 5 times cosine of 2t inside of there. So this is an oscillatory function. The ball is undergoing some type of simple harmonic motion. right? How is it doing that? I don't really care right now, right? This is just to show you the example as to how nice derivatives can actually be. Well, on your equation sheet, you're going to see something that looks along the lines of this d over dx. So that's derivative, d for derivative, essentially, right? And you're given a bunch of different functions. So what you're probably going to see is something like cosine of, I believe it says kx, maybe it's ax or nx, k, a, n, right? Those are just constants. The thing we care about is the x, right? So we're taking the derivative with respect to x. D over dx says take the derivative with respect to x of cosine of kx. So we treat k as a constant, and then we just focus on the x. But again, on your equation sheet, it tells you that the derivative is going to be negative k sine of kx then. So essentially what happens is you're changing this cosine to a sine, and then you're pulling this k value outside of the sign and multiplying it by -1. And I know that that seems kind of weird, right? You're probably just like, where the heck is this coming from? That is something that you are going to cover in your calculus class. That is not, you don't actually have to know how to compute these derivatives from scratch or prove these in Physics C. I think the important thing for you to do, and I really do like to emphasize this, the important thing is just to understand, when do you have to take a derivative, which rule do you need from your equation sheet, right? Well, in this case, position is a cosine function, and there's only one rule on your equation sheet that has a cosine where you're taking a derivative of a cosine function. Right. The other ones are for polynomials. There's one for a sine function. There's one for an exponential. There's one, I believe, for natural log as well. They're all pretty distinct functions from each other. So it's typically going to be pretty obvious which rule you actually have to use. So if I wanted to take this position function, I actually wanted to find the velocity of the ball at any point in time, all I have to do is take the derivative of that. Using this rule right here, we end up with the velocity as a function of time. And I'm actually going to write it above the problem just so I don't have to try to create a new page. Velocity as a function of time would be -10 sine of 2t. Why is it 10 instead of 2 out front? Well, it's because you have that extra 5 by the x. Anytime you have an extra coefficient that the formula sheet rules do not give you, that coefficient stays there, and you just multiply the result by that coefficient. So I can essentially ignore that 5. I could just take the derivative of cosine of 2t with respect to t, right? Not with respect to x, but with respect to t, because we're doing time derivative here. And I would get -2 sine of 2t. But then I would multiply it by that extra 5 that we dropped at the beginning, hence where the -10 comes from. I can do the same thing with acceleration. You can check your equation sheet for this rule. But one thing that I want you to feel comfortable with, so please try this on your own as well. Let me know if you're not sure, is that the acceleration would be -20 cosine of 2t. Now, for example, let's say that I have traveled for pi seconds. I could tell you the velocity of the ball. It's going to be 0 because sine of 2 pi is 0. I could tell you what the velocity is going to be at pi over 2 seconds. In that case, the velocity is going to be -10 meters per second because sine of pi is, that's 0 actually, I apologize. Time t pi over 2, you're going to have 0 as well. Sine of pi is still 0. Oops, there's some bad math there. If I take pi over 4 seconds, though, if I take pi over 4 seconds, the velocity would be -10 meters per second because you would get -10 sine of pi over 2. Sine of pi over 2 is 1. Multiply that by -10 then. You could do the same thing with acceleration then as well. And it does actually go the other way as well, where you could actually calculate position as a function of time by taking the what we call the integral, which just refers to the area bounded by the time axis for the graph, right? So if I wanted to take the area underneath my graph bounded by the time axis, that would be what this little squiggly function thing that I just drew was. Right, so the way that I read this is x position is equal to the integral, the area underneath the velocity function with respect to time. You can think of velocity as being the height of your graph, and then dt is essentially the width. So you're essentially taking this graph, taking the area underneath the graph, chunking it up into rectangles, and getting an area out of it. And much like derivatives, the rules for those are also on your equation sheet, which is good because that means you do not need to try to build these away from scratch. And then likewise, velocity is the integral of acceleration with respect to time then too. Now, here's something interesting I want to show you then. We have a couple of kinematics equations. Let's start off by saying that, let me essentially just formulate this as an example. So let's say that a ball is moving in one dimension with constant acceleration a. It starts with initial velocity v with a subscript of I at a position of x is equal to 0 meters. And what we want to do is we want to find velocity as a function of time and position as a function of time. So essentially what we have is the ball always has a constant acceleration. So a as a function of time, acceleration as a function of time is just a. Well, as it turns out, I could find the velocity as a function of time by taking the integral of that. So velocity as a function of time would be integral a dt. But according to my equation sheet, if I integrate something with a power of 0, which is all a constant is t to the power 0 multiplied by that number, right, then I end up getting that same constant multiplied by t to the 1 power. So I end up getting a times t, but I'm not done yet because I have to add some sort of constant to this. That constant appears because if I integrate and then I try to take the derivative of whatever I just got out of that integral, the constant is going to go away. The derivative of a constant is going to be 0. So when you're taking a derivative, you lose a little bit of information, even though derivatives are easier to take than integrals. So when you integrate, you essentially have to add this weird constant here just to account for the fact that the particle might not have started with 0 initial velocity. How do I find what that is? Well, I could say that the velocity at time 0, so plug in t is equal to 0, was equal to vi, and that's equal to a times 0 plugged in for t plus c. So therefore, that value of c is going to be equal to the initial velocity. And look at that. That means that the velocity as a function of time is given by the initial velocity plus a times time. That's actually a kinematics equation. Final velocity is equal to initial velocity plus acceleration times time. If you do the same thing with position, what you're going to find is that x of t is going to be equal to vit plus 1/2 at squared. Another kinematics equation. Displacement is vit plus 1/2 at squared. Now, I want to emphasize something. This is something that should have been heavily emphasized in your physics class when you took AP Physics 1, but the kinematics equations only hold for constant acceleration, right? If the acceleration is varying as time goes on, you can only use the calculus definitions. So for example, let's go back up to this cosine problem. The ball moves along the x-axis with a position given by 5 cosine of 2t. Well, if I wanted to find the velocity and the acceleration, I cannot use a kinematics equation for those. You'll notice that I just immediately took derivatives to find velocity and acceleration. And the reason why is because the kinematics equations you derive them from each other by assuming constant acceleration, right? We just saw that you only get the kinematics equations back if you have constant acceleration. But as soon as acceleration starts to vary as time goes on, then when you take the integrals of those functions, you are not going to get functions that you recognize from AP Physics 1. And so essentially, the kinematics equations come from these calculus definitions. They are a specific case that only holds for constant acceleration, right? So if you want to have sort of the general case in mind, right, the important thing then is to note that the calculus always holds, but the kinematics equations, those 3 or 4 equations, right, that we learned back in AP Physics 1, where you have 4 variables in one equation and then one kinematics quantity that doesn't matter, right? Those only hold when you have constant acceleration. And again, they're just special cases of these calculus definitions that we have talked about. All right. So that is the important theory behind what we have with representing motion, and in terms of talking a little bit about displacement, velocity, and acceleration. Right. A couple of other little important points that aren't, they're just kind of like here right now. But we'll see them with some examples. Is that when an object is in free fall, right, the acceleration is a constant acceleration, and it's given by -10 meters per second per second. What College Board has actually come out and said is that they expect you to use 10 for g. However, you are not going to be penalized for using 9.8 or 9.81. So you can be more accurate, but they don't expect you to be, right? You're only expected to be as accurate as 10, and the numbers will typically work out a lot nicer there. So I think it's to your benefit to stay with 10 then. In addition to that, the other thing would just be that there is another kinematics equation that doesn't really appear when you're doing this calculus. Some of you probably remember VF squared, and actually, I'm just going to write it out so it'll look a little bit nicer. You might remember the VF squared is equal to VI squared, final velocity squared is equal to initial velocity squared, plus 2 acceleration times displacement. That, again, only holds for constant acceleration. That is a kinematics equation. You cannot use it when acceleration is varying as time goes on. In that case, like the only thing that you could do with the kinematics equations is use average acceleration, because average is designed to be a constant value for these with the definitions we have, but there's no point to it, right? I can't see a situation where you're given a non-constant acceleration and then asked to use the kinematics equations with it. It would essentially be a waste of time, right? If you're given a non-constant acceleration, the entire purpose of physics C is to be able to describe its exact motion using these calculus definitions. All right. So in summary, you need calculus to talk about the full relation between velocity, acceleration, and position, right? Derivatives represent essentially like slopes, they're divisions, whereas integrals, the squiggly looking thing on the right side next to the graph here, those represent multiplications or areas. So you can still say that displacement is the area under the velocity time graph, but we typically just say that's the integral of the velocity with respect to time. Likewise, derivative, you could still say that velocity is the slope of the position time graph, but we tend to still say that we tend to just say it's the derivative of position with respect to time. And all of that being said, then again, the very important point, and I know I've said this a few times, but I just want to say it as this last kind of point in the summary. You cannot use the kinematics equations everywhere. You can use the calculus definitions everywhere for velocity, position, and acceleration, but the kinematics equations only hold if your acceleration is completely constant across all points in time. All right, I think in the next video, instead of going on to topic 1.4, we are going to take a look at a few more examples. So, I advise you to get your equation sheet out as well. You can just search on Google AP Physics C equation sheet if you need it. Use that to kind of follow along as we go through some examples as well, right? Check to see that the examples that we did in this video also make sense before you go on to the next video too. And yeah, we'll see how you guys are feeling with those calculus in the next video too. Hopefully, after seeing a few more examples, you'll feel a little bit more comfortable with it. And then after that, we'll go ahead and move on to two-dimensional motion, and that'll be the end of kinematics. It's a fairly short unit. All right, thank you guys for watching. I will see you in the next video now.